During the monsoon, South India faces high-intensity rainfall that frequently leads to uncontrolled flash floods. These deluges routinely overwhelm modern roads and submerge entire agricultural districts. Within months, the same landscape turns arid. Severe droughts crack the soil, leaving the region desperate for the water that was flowing through it only a season prior. Modern civil engineering often struggles with this oscillation. Brute force solutions like concrete storm drains and deep wells frequently fail to manage such rapid shifts between climate extremes. Survival here requires a specific type of engineering, a single system that drains a flood while simultaneously stockpiling that same water for the drought. Over a millennium ago, the Pallava dynasty managed this environment while ruling along the coast of South India. They utilized advanced stoneworking techniques to carve massive, intricate monuments directly out of the coastal bedrock. Their structural masonry projects, like the shore temple at Mahabalipuram, were engineered to withstand the direct impact of the Bay of Bengal for 12 centuries. But their most significant contribution to the region's survival moved away from granite. It used a combination of mathematics and geography applied directly to the dirt landscape. How did a dynasty known for immovable stone monuments design a dynamic, region-wide water grid that keeps these valleys fertile today? The Pallava system centers on the Eri, an artificial lake. Under King Nandivarman, engineers constructed massive catchments like the Kavaripakam tank at high elevations to intercept water early. This topographical map illustrates the strategy. By placing catchments in high-elevation basins, the Pallavas captured monsoon rains before the water could gather destructive speed as it flowed into the lower valleys. To contain this volume, they built thick embankments of packed soil. These walls had to resist the compounding pressure of millions of gallons of water as the levels rose during a storm. Static reservoirs carry inherent risks. If water reaches the top of the embankment, pressure causes structural failure, turning the stored supply into a destructive wave. The Pallavas solved this risk by transforming these static lakes into a non-overflow grid. Engineers surveyed the landscape to find the exact threshold where the water pressure would become dangerous to the earth banks. They carved precisely angled spillways just below this critical point. When the lake fills, gravity pulls the excess water into these channels rather than allowing it to put pressure on the main dam. These channels route the water overland to a completely separate, lower elevation area miles away. Once that second lake reaches capacity, its own spillways activate. The water drops to a third lake, and then a fourth, cascading in a controlled sequence down the regional slope. This stepped movement across the terrain continuously bleeds off the kinetic energy that typically makes monsoon runoff so destructive. By utilizing topographical momentum, the Pallavas converted the force of a flood into a controlled, life-supporting water supply for the agricultural valleys. A macro-level view of South India reveals the scale of this engineering. Thousands of interconnected eras form a massive grid-like footprint across the topography. This network functions as an operational 2,000-year-old machine, remaining vital to local agriculture today. Modern infrastructure often relies on concrete barriers and motorized pumps to dictate water movement through mechanical force. These systems require constant maintenance to resist natural forces, whereas the Pallava grid is designed to yield to them. The Pallava grid suggests that infrastructure reaches its peak efficiency by designing systems that perpetually collaborate with the environment's own energy.